So I'm a PhD student at Brown.
Yes, I realized that wasn't turned on.
All good. It's just always a little scary when that electronic voice comes in your head. So you most likely know my advisor, Will Creighton or Shriram Krishnamurthy, but I'm a PhD student at Brown, advised by these two. And today we're going to talk about AquaScope. So AquaScope is a tool that automatically generates diagrams with the goal of sort of connecting the dynamic and the static semantics of ownership. And this was intended as like an education project a little bit, but a lot of fun PL and sort of static analysis bits embedded into it. So in this talk, I will put little like purple asterisks in the corner of a slide that I think has a particularly salient key idea in it. I'm also not super accustomed to just like talking at a screen for 60 minutes. So if you have a question or comment, just like feel free to butt in, like unmute yourself and talk. That's totally fine. I would much rather it be a discussion about how we can take this idea and sort of expand it into other areas of formal methods and try and get the education space bumped up a little bit there. So yeah, let's do it. The context for this is that ownership is difficult according to people who use Rust. Now this survey is a few years old at this point, so these are from like the Rust survey of 2020, but 60% and 50% of respondents found lifetimes and ownership very tricky. And I learned Rust at one point, and to me it was like, well, isn't ownership kind of intuitive? And if you dig through Nico's YouTube videos like 8 years ago, you get these fun little YouTube clips like this where you have some orange character who owns a book, and the blue character on the right wants to borrow that book. And so the orange character, of course, is going to like lend the book out with the expectation that the book comes back after some period of time intact, right? If the blue character took the book and then like burned it, that would kind of be socially frowned upon and sort of mean. And then the orange character wouldn't want to lend her books to the blue character anymore. But it feels like ownership should be socially intuitive to people. And yet, developers still rate ownership and lifetimes as being a very tricky language concept to learn in Rust. And so when I say intuitive, or like on the previous slide, when I said intuitive, I'm kind of baiting myself a little bit, because as like researchers or programming language designers, we might think, oh, this language feature is super intuitive. But per like the definition, like the dictionary definition of intuitive, that requires that things have, immediate apprehension without any reasoning or intervening processes. And in programming, like, I don't think there's anything that, covers that bill. Like everything requires some bit of reasoning or some like intervention process in order to understand it. And so describing a feature as intuitive might be a little, it's very wrong. So even ownership, which might seem intuitive, is not intuitive. So the goal of this work is to systematically make ownership types easier, to learn, sort of the end of that sentence. And we do it with 3 steps. So the first step is we actually want to understand the misconceptions of ownership. So why do people find ownership difficult? What are they struggling with? And then the second step, of course, is to design a pedagogy or like, a set of learning materials to address these specific misconceptions that developers have. And then, as all good research does, like we should compare that new pedagogy against some baseline to actually ensure that we've improved things and not just, speculated and then made things worse or not improved.
It might be
we want to actually make sure that we improve.
Good to make it the separation between old and new more explicit.
So I guess old being, in this case, the current materials, and then new being we design some new pedagogy. We're going to release those materials and give those to new developers and then see how they, improve with learning outcomes. Does that make sense?
Mm-hmm.
So like you could even think about it as like version 1 of a textbook. And then if you rewrote the second version of a textbook, do people learn better from that second version, or was the first version actually better in sort of a sense? And so in this case, we have a fork of the Rust programming language textbook, which is what we're actually using for all of our experiments here. And I'll talk about that in a little bit. Ooh. So In this talk, though, I am mostly going to focus on sort of that second point in that list of three, partly because I'm not so much of an education person as Will and Sriram are, but I like building things with compilers. And so that designing a new pedagogy is sort of where all of that stuff comes in. So we're going to spend most of our time there. But of course, like I want to go through the whole story just to make it complete. If you do want an even more thorough treatment of those education bits, Will has given a talk at OOPSLaw and Iwako, and then like you can also read the paper that we published in 2023, which has all of the details of everything that you could ever want in relation to this project. So, so the first step is to try and understand the misconceptions that developers currently have. So to do that, we go to Stack Overflow, which is where confused developers used to go. Not so much anymore, but we still have good Stack Overflow questions available. And here, so we can see this person asks, in the following code, how can I return the reference of floor instead of a new object, right? So they have this function, and they have, two owned big integers, and then some floor, which is a reference to a big integer. And in the, my slides got a little messed up, but in this else branch, that might be too small to read, but they clone the floor in order to return it as an owned value, when in reality, they want to return either an owned value or a reference. And this is a good question because it represents some misunderstanding of lifetimes, like a common misconception. So what we did is we took all of these questions from Stack Overflow and sort of binned them into 18 categories of very specific misconceptions. And then we took those questions and we simplified them. So here we have this make separator function, which has the exact same functionality as that previous slide. It's just a little simpler. We're using strings instead of big ints. And we say, okay, if the user string that's passed is the empty string, then we're going to create some default separator with 10 equal signs. And then we want to return a reference to that. And of course, we can't do that because the reference to default, we're referencing some stack variable. And after you return from the function, that would be a dangling pointer. But the idea being that we want to somehow get people to answer questions about this specific piece of code. And so in our study, we embed these, we take these 18 tasks, and for each piece of code, we have 3 questions. The first question is, what error message would you expect from the compiler? The second question is, if the compiler didn't reject the function, what is the, a program that would violate memory safety if one exists? So we're asking them about like the undefined behavior the compiler is trying to protect them from. And then the third is, what would be an idiomatic fix to this function? Now, for each of these questions, like the first one, we would expect somebody to say, well, the returned reference at default doesn't live long enough. For the second question, you would have to call make separator with the empty string, and then you would crucially have to access the return value of the function in order to dereference the dangling pointer. And then the third one, we were a little lenient on this. So if you like returned an owned string instead of the reference to a string, that would be fine. Of course, like the actual idiomatic fix would probably be a copy on write pointer. Still learners though, so we give them a little bit of leeway. Any questions about these, like the setup here? So we've got these 18 questions that represent common misconceptions related to ownership. And then we have these 3 questions targeting, what is the compiler going to tell you? What undefined behavior would exist? And then how do you fix it? All right. So we will move forward. So what we found is that learners can predict the error message in 64% of cases. So like that's pretty good. 64% of the time they can say, oh, this is what the compiler is going to say. However, the more concerning number is that in 31% of cases, they can actually write a counterexample that would produce undefined behavior. And then even less than that, only 15% can actually justify why their counterexample is, would cause undefined behavior. So, and then, for actual like idiomatic fixes, people, like the typical Rust learner thing, they just clone everything. So here's some example function where we have a struct. This is for like a, like you can think of this as like if you're a professor and you're grading a course, you have a struct and you call a method called getCurve, which returns just an option to one field of that struct. And then after that, you want to iterate over another field of the struct, a vector, and you want to increment all the scores in that vector by this curve value. Now, knowing the implementation of the method getCurve, I know that this function wouldn't ever, experience undefined behavior because you're only ever accessing two separate fields of the struct. But of course, you need to rewrite it such that the Rust type system can actually, understand that as well. But what we found is that people will just clone it, right? So if you have, you can't access scores, so I'm just going to clone it and then iterate over that. But of course, this is now iterating a new vector, not the one in your actual struct, and then that memory is dropped right after this loop. So your program is now incorrect. So not only is this not really idiomatic, it's just a wrong fix. And looking at sort of
sorry,
yeah.
question.
Yeah,
Does this even compile? I would expect a borrow error because curve is still borrowed across the clone. Or does it work because it's all immutable borrows?
Curve is an immutable borrow, so that would be fine.
Okay. All right.
Yeah.
All right. Thanks.
So the statistical analysis shows that if you got question 1 correct, so if you can predict the compiler error message, you were only 1.1 times more likely to actually get question 3 correct, meaning that you were able to fix the program. But if you got question 2 correct, then you were 2 times more likely to have an idiomatic fix. And what that tells us is that, wrong button, that if people can connect the dynamic and the static semantics of ownership, then they're much more likely to be able to fix problems idiomatically. So they run into a borrow check error, and they can say, oh, this is actually like unsoundness, or this is actually undefined behavior that the compiler is protecting me from. And so I know how to fix it because, I know what undefined behavior the compiler is protecting me from. Questions so far?
I actually do have a question. I mean,
Yeah, go for it.
You mentioned that the model you're saying so far is that people understand what undefined behavior is better than they would understand the borrow checker, or like in some sense, like that people have a useful model of it. Is that true of average programmers, or is it just a nebulous concept to them, almost the same way that borrow checking is?
Yeah, so this is a good question. So maybe I was a little unclear. So people were only able to write a counterexample in 30% of cases, and they only understood their own counterexample in 15% of those cases. So what that means is people do not understand the undefined behavior, right? And that's because a lot of the developers that are coming to Rust only have like Python and JavaScript experience. So if you've never run into a seg fault in like C++, the node like memory safety isn't really something you've ever had to worry about. And so dereferencing a dangling pointer after calling a function is a totally foreign concept to you. And so the whole point of this work is that, like, as we're going to talk about in just a few slides, is we want to show people the undefined behavior that would occur if their programs were to run, even though they don't type check. Does that answer your question a little bit more?
Yeah, definitely a bit more. Yeah.
Okay, awesome. And so to be a little bit more precise, when I say dynamic semantics, like people need to understand the dynamic semantics of Rust. That is, they need to understand the undefined behavior, like I just said, like the compiler's protecting them from. And when we say static semantics, we want them to understand when the type checker is, protecting them from genuine undefined behavior, or if it's just an incompleteness in the type system and their program would run okay, but the type system's just not quite smart enough to figure that out. Both of those cases are a little bit distinct. So we want to be able to teach people how to get their programs to type check when they, it's just the incompleteness of the borrow checker versus they're trying to fundamentally do something unsafe and the borrow checker is actually, telling them something really important. All righty. And then there's this question, though, of if we're teaching them about the dynamic and static semantics, how much do we actually need to teach them? So we can think about this as like a ladder of abstraction. At like the most abstract, we can say something like Rust prevents memory errors. which of course is, like it's a correct statement, but it's not particularly useful if you're trying to reason about a borrow check error. You can drop down a little bit and like be a bit more specific and say, well, Rust enforces aliasing XOR mutability. We can, go down the ladder a little bit more and start explaining how Rust does this. And we say, well, Rust tracks the live range of borrows. Again, this is sort of an imprecise English statement, so we can start providing some math and say, like, this is precisely how it works. And then, if you're a compiler engineer, you can actually just go read the source code for the borrow checker and like really understand exactly how it works. And so the question is, how far down this ladder do we need people to be in order to fully understand, like to connect these dynamic and static semantics? So what we found, these errors are really small. What we found is that people are somewhere up here. So they're kind of near the top of the ladder. They understand that Rust prevents memory errors, and they understand that, yeah, you can have aliasing XOR mutability, but we really want them down kind of here around the mechanistic level of Rust tracks the live range of borrows. We don't need them all the way down to like the math formalism. That would definitely be infeasible if you've ever tried to like teach a friend something like that. But we do need them to understand a little bit of how Rust does this so that they can catch those cases of when Rust is preventing undefined behavior genuinely statically, or if it's just an incompleteness in the type checker. All right. So there is an asterisk in the corner of this slide. That means there's a key idea here. And there's two key ideas. The first is when you try to embed your tool with WebAssembly into your slides, JavaScript doesn't always compose. So we're actually not going to be able to do that in the slides. I'll come over here and use the playground that we have published. But the published versions of these slides will have some embeddable instance. So this is we're first going to look at the runtime diagrams that I'm talking about here. So here we have a simple function. We're creating some vector. It's mutable. We're then going to, borrow or create a reference to the first element of that vector. Then we try and push an element onto the end of the vector. And then we try to access that reference that we created on line 3. Now, if we look at the runtime diagram here, so at like step 2, we create some V on the stack, which points to some memory in the heap. Then we, at L3, create the reference to that heap location. L4 is when we push onto the end of the vector. And this causes, we can assume that this causes the vector to reallocate. Maybe it's overflowed the capacity that it had. And then when we try and dereference n, that reference, the previous immutable borrow, that would be undefined behavior because the pointer is being used and it no longer points to valid memory. And so this is sort of the level of abstraction we're trying to get people to think about. Of course, this isn't how Rust actually works, right? V or n might, end up in registers. They might never be on the stack, but those are all details that we don't need people to understand. We kind of just need them to get an abstraction level similar to how Miri works. And of course, like these diagrams are generated using Miri. So it's actually relatively easy to translate that model over to these diagrams. Any questions on this diagram here?
I would be extremely curious to hear how you're getting this out of Miri, but maybe that's for later.
Wait until the next slide. So I won't go into too much depth on exactly how we get it from Miri, but I will talk about things that like Miri can do to facilitate building tools like this. So just one point I'll make before we get to that slide is that counterfactual reasoning. So if we were just to ask people, the question 2 essentially from our quiz, which is, what can go wrong if you run this code? So developers then have to engage in counterfactual reasoning, which is, okay, if I did run this code, what would happen? And it's much easier to just show people what would go wrong than to force them to sit and think about it. Now, of course, the thinking process is good, which is why we ask these questions. But a diagram is also better. Like you can just generate the diagram and show them exactly what would go wrong. And so I label this as a key idea because I think there's a lot of things in like verification that could benefit from some sort of counterfactual reasoning like diagrammatic notations or, counterfactual examples of like, oh, this method doesn't verify. Here's why. Here are inputs that would violate, whatever constraint.
Okay.
Yeah. Was there a question? All right. I will move on. So to Ralph's question, which is how can the compiler help? Well, the first thing that I'm going to
Can I
like
ask
try
a
out.
previous
Oh
question
yeah,
though?
go for it.
So,
Please.
Tony, if we didn't, so the local invariance, is that only for like weird protocols that change their state without looking at messages? Or are you using that in most of your examples?
Sorry, could you repeat that? I don't think I understood the question.
Where does Paxos use it?
I don't think the question is for
I think
you.
I think I think someone is not muted and has a different conversation. Can someone mute Brian?
Gotcha.
Thanks.
Yeah.
Like we're not using Paxos. Okay, so how can the compiler facilitate sort of tools like AquaScope? And the first thing that I'm going to say multiple times for the rest of the hour is make APIs public, or make some API available. If you think you're hacking on the compiler and you think, this function, nobody else might need to know this data. It's just going to stay private within this module. You might think some researchers at Brown might want to go in and actually scrape that data to create some visualization or some tool on top of the compiler. So public APIs are always a good thing, at least for us. For example, so the version of AquaScope that is currently published is like a year old. And part of that is because as Miri has been moving into Rust const eval, some of the things have gone from public to private. And that's made it a little bit trickier. So this version of the playground here I'm running, which actually compiles to WebAssembly, we maintain our own custom fork of the compiler where we've kind of just made a bunch of things public and then also supported compiling to WebAssembly. And then lastly, public interfaces allow us to spend more time working and less time just, filing PRs to the compiler to make things public. Any questions? All right.
Very minor question. Sorry about the previous slide. How many of those PRs making things public do you file?
Good question. So the answer is, for this specific tool, we haven't filed a PR in a while just because we've been working on some other tools. And the tools that we're working on currently use like the new trait solver. So I've been working with like some people of the types team to make some of those APIs public that we can hook into. There is an impending PR that will try and make a bunch of things in Rust const eval public so that we can get off of our custom fork of the compiler, because I do not like being in the business of maintaining custom Rust forks. It's a very painful experience. I don't know how much Crusoe.
I would say I'm making many of these private because there's some complicated invariants and I don't want people to screw them up.
Yes.
But this is like a case-by-case thing, and in particular for read-only access, which should be enough for you, I guess.
Yeah.
I mean, just let us know what helps, and then we can talk about it, I would say.
Yeah.
There's obviously no promise that this won't change tomorrow. Like we're going to refactor the APIs whenever we think that's good for the compiler. So you will might still have to update things, but at least you won't need a fork.
Yes. Yeah. I don't want to say that never change the APIs, because the Rust compiler needs to change and the APIs need to get better internally, and we always have to work with that. But yeah, we will be in touch shortly, probably about how we can change the Rust const eval visibility modifiers there.
Sounds good.
Awesome. Okay, so moving on. So that's like the runtime diagrams. As diagrams themselves, they're not super interesting, right? It's kind of what you would draw on a whiteboard if you were a teacher, or if you were explaining the evaluation process to a friend or a student. they're not overly detailed, but they are sufficient in order to understand the model of evaluation. Now, the static diagrams are a little bit more novel in this sense. So we're just going to go through the same example, and I'll point out the different pieces of these diagrams, and then we'll actually kind of dive through how they work, a little bit of the math of, like how AquaScope does this, and then we'll continue from there. So what we did is we created this model of ownership, which we call the permissions model. So every path has either a read, write, or own permission. So for example, when we assign to V here, V gets read and write and own permission. So the little pluses next to those characters mean that they have gained permission. Then when we come here and we create the immutable reference, we lose write and own permission on V because we can no longer mutate V while that loan is live. And then to N and the memory behind the reference star of N, we've gotten read permission. And then of course the pointer itself has own permission because it can drop itself. Then we come down here and we try and call v.push. And these two little characters in between, or like to the left of the dot, mean that these are required permissions in order to call the push method. So we need read and write permissions. And the W is hollow because V does not have write permission, right? We lost it right here. And so any hollow dot or hollow character is a borrow check error. And we call those permissions errors. All right. Any immediate questions on the diagrams, just so that everybody understands them before I dive into the different parts? All right.
What do the arrows mean?
What do the arrows mean? These arrows.
Right.
Good question. So I will talk a little bit about the evolution of how these diagrams actually came to be. So these arrows represent the action that caused the change in permissions. So this first arrow, if you hover over it, it says the path is initialized here. So this is when we first assign V, we get those permissions. This second arrow, or like the arrow going to the right, means that it was borrowed. And so, V already existed before this point, and the borrow is what's causing the change in permissions. And then of course here, like, N is getting assigned here. So this is that initialization arrow. And then we have a few other arrows that signify like regaining permissions. And if you have like a liveness analysis and the variable is dropped, there's also a different character for that.
Thanks.
But this isn't like, yeah, so it's a good question because these are not necessarily perfect, right? I don't think arrows are, to go back on my prior point, like intuition is not necessarily what we're relying on here. We kind of expect people to hover over them. And designing an iconography that will actually capture the actions that are going on is quite difficult. People perceive the icons very differently. Okay, so the static diagrams is how it works internally is there's like one permissions framework, which will go ahead and compute all of the permissions for paths at specific mere code points. And then we create two static analyses on top of that. So we kind of created our own permissions API internally, and then use that API to create these static analyses. And there's two distinct analyses here. There's one which we call boundaries, which are these like inline characters, which specify when a permission is required. And then, of course, like if it's missing, they're hollow. And then we have a second analysis, which we call steps. And these are the tables onto the right and signify like how the permissions change with each line of code or with each operation. So we're going to look a little bit into those a little bit more specifically. So the core analysis, which just computes all of the permissions, is super simple. It's like kind of just one file. It's a few hundred lines long, and it boils down to a handful of data log rules. So we have rules like this path cannot write at this point if there's some loan that conflicts with the path and the loan is live at that point, for example. And of course, like these data log rules piggyback on top of the Polonius model. which we pull out. And so the key idea here is if you create a good like API, so I believe that Polonius is a pretty good API, and then we then build our permissions model on top of Polonius to create another good API, you can really facilitate building cool tools like AquaScope much better. The full rule set is actually in the documentation and on GitHub if people want to look at those later. So again, like how can the compiler help or facilitate tools like AquaScope in this case? Again, like make APIs public. So Polonius is a great example. And I think a lot of tools use Polonius because of, for that reason. Like if you try and interact with the borrow checker outside of Polonius, it's very painful, but with Polonius, it's very nice. I like to think about compilers as more of a database. So you have some set of facts, and then I just want to query the compiler about those facts about different code points. And I think Polonius does a very good job at this. Another thing is like, if we had a stable mirror API, that would be really useful, right? Every time we update our tools, the biggest pain point is just then tackling all of this tiny changes here and there throughout the mirror and the type system, and having some stable mirror that would give me the confidence to update the tool chain a little bit more frequently without it being like a nightmare process of a week long, would be absolutely wonderful. And I'm sure it would really facilitate other tool, verification tools, etc., that also work across the mirror. Any comments so far? All right. So one important thing about our permissions analysis is that it's not we didn't reinvent the borrow checker. It's really just a reformulation of the borrow checker rules. So here is an example of like a rule you would write for the borrow checker itself. So we have like some access error G would be if there's a lone live instruction I, but that lone P prime is invalidated at I, and that's because there's some path that's written at I, and the path P conflicts with the path P prime. That's kind of how you'd write it. And then our permissions model just reformulates that like this. So we say there's a permission error G if the path P needs like a write permission at I, and we know that because P is written at I. And then we say, well, P is missing write permission at I if there's some lone on P prime that's live at I where the path P and P prime conflict. So we haven't reinvented anything here. We've just shuffled them around, which is why our core analysis is just a handy set of data log rules, because we really just infer a little bit more about the environment, but we haven't had to do much work, to re-implement the borrow checker, which would in itself be a nightmare. So moving forward and looking at this code, we have, this is our like vector code on top, and then here's the error, like the diagnostic that the Rust compiler would give. And we say, of course, can't borrow V is mutable because it's borrowed as immutable. The compiler will point at where the borrow is created. Then we point at where the mutable borrow is created, and then we like point at the last use. I believe there's some terminology for this in the compiler of like the 3-point diagnostic approach or something like that. But the way that we kind of like to think about it is, what would a learner, or really just any developer, ask about this error? And again, we return back to that counterfactual reasoning. So why is the write permission required? And why doesn't the path V have write permission? So to answer question 1, this is that boundaries analysis that I mentioned first, which is, why is write permission required? And it's because the push operation requires write permission. And then why doesn't W have write permission, or why doesn't V have write permission, is answered by that steps analysis, which are those tables off to the right. And this is actually why we have both of them. They didn't both always exist, but we noticed that people kept, they could answer question 1 with the boundaries analysis, and then we were like, how can we actually get them to answer question 2? And it was with the steps analysis. We've already talked about the boundaries. So like I said, there's just these little stacks in between the operations, and this is how people can tell why a permission is required. You can imagine a version of the tool where you actually hover over this W and it will show you the type signature of push and say like, oh, well, you know, the receiver type is the @mute self, and so this is why the write permission is required. We don't do anything that elaborate because it's quite visually noisy, but it is possible next work. And then the steps analysis is actually kind of what I want to talk about for just another minute or two. And that's these tables on the right, because so we implemented this steps analysis about 4 separate times. And that might seem not obvious why. So if you were designing an analysis like this, you know, you have access to the mirror, and that might look something like this. So basic blocks 0 through 3 is all of the prelude code to initialize the vector, right? And eventually we allocate the vector and assign it to _1, which represents that variable v in the source code. And at this point is when we would gain read, write, and own permissions. And then like we go on to basic block 4 if that doesn't panic, and we take the immutable reference to 1, but that's in order for us to index into the vector. And then in basic block 5, we have to sort of reborrow in order to get our reference n. And what we want to do is we want to take the difference in permission states between operations. But we only have access to the operations at the mirror level, and we really want to show that at the source level. And I quickly learned that source mapping information from the mirror to the source Rust code is extremely difficult. So that is why it took us a few implementation tries to get it correct, because you never want to leak a permission. So when you're creating those diagrams on the right, you want to make sure that every change in permission accounts for all of the permissions in a function. So from like start to the end of a function, your net permissions gain and loss is 0. So of course, in this example, we can like draw the braces roughly around where these source permissions occur. So basic blocks 0 through 3 are all just for this first statement. And then basic block 4 and 5 kind of correspond to the second statement, and so on and so forth. And things get really tricky when you have like branching and loops involved. Yeah, any questions about this? I don't want to go into too much detail because it's very superfluous, but it is a interesting thing that I think most tools have to account for is, you know, source mapping information from the mirror back up to the source code. All right. Yeah. Okay. So I'm going to switch presentations just a second because I want to talk about the evolution. Where is it? All right. So can you all see a picture with a bunch of triangles and circles and stuff on it?
Yes.
Awesome. Okay, so what I've been showing you is the final product of AquaScope, but that was developed over several weeks. And this right here is the original concept that Will and I had, which was how can we represent ownership in a diagram? So the key takeaway from here is like, don't ask your PhD student to just draw a diagram and come back to you because you'll get something that looks like this. And it won't be super helpful. But the idea was color represents the ownedness of a value. So everything that is red is like an owned value. And then everything that is blue represents a set of loans to a type. And then the shape is the distinct type here. So I believe, if I remember correctly, like triangles are strings and squares are options to strings, and then the circle is the option. And this wasn't like a total waste of time because we did, like it morphed into these permission boundaries where we have the colored circles in between the operations. Of course, this diagram is drawn is not a winner, but ideas do evolve. And so one of the things that we started out trying to do was how can we map the type system of Rust to visual marks such that when there's an error, the visual mark makes it obvious. So here we have like a rough type lattice of, the immutable borrow is at the top, and you can pass an own value if an immutable borrow is necessary. If you have immutable borrow, you can convert that into an immutable borrow. And then at the bottom, you have like a mutable own value, which is a little bit different than the others because there isn't really a mutable owned type. The mute is on bindings, but we'll ignore that for just now. And the basic idea that we had was if we could represent ownership as like hatching and then mutability as the color. And so then we generate all of the possible combinations of requiring one ownership versus like what mutability. And we got diagrams that look kind of like this. And the rejected programs on the right aren't necessarily visually distinct from the programs on the left. So we decided that's not obvious, so we're going to iterate a little bit more. So the second version of this, we split out those we split out the types into two visual channels. So the ownership is represented by the fill in a square, and the mutability is represented by this fill in a circle. So now, if we generate all of the possible combinations there, we can see that the rule is that if a shape is hollow, then there's an ownership error. And so if people want to learn how to read the diagrams, they only have to run one rule, which is a shape can never be hollow. And this kind of evolved into, of course, these permission boundaries that we have today. We first experimented with like shapes, sticking with the squares and circles. We tried a bunch of icons from Font Awesome. That did not pan out very well. We then moved on to letters, which we started to like a little bit more. We then stacked them to save space in the code and try and reduce visual clutter a little bit. And then eventually we created these morphing letters so that we can hide the permissions behind these circles. And then when people hover over them, you get the full letter. So the circle is a little bit less visually like disturbing to the code than the characters, so we don't want to show them all by default. Questions about this process? Like, neither myself nor Will is like a visual researcher, so this was quite an experiment, and I think it's kind of fun to go through and try a bunch of things to see what resonates and like makes for an easily visual experience.
So I have a question on that side. You say you tried all these things. How did you validate your trials? Is it just you guys, like between you two, or did you do smaller studies?
Yeah, that's a good question. So most of these was between us because, if we really don't like something, then it's quite likely that other people don't like something. So we didn't want to waste time and money trying to validate something that we thought was bad. And then we didn't really go on to validating it until we found the design that we liked. So to your point, like maybe these icons in the bottom left would be the winner. I would be skeptical of that because I don't think they make for a very obvious like reading experience. But without a user study, that would be hard to validate. You're correct. And then, after we created these the permission boundaries, we eventually moved on to those permission steps diagrams that we see on the right. Now, let me just skip forward. So there are actually a few more iterations that I'd like to talk about. So the first is how the own permission interacts with the copy trait. So here we have a vector of strings, and we, same as before, like we create the reference to that first element in the vector, and then we try to move out from behind the string. Of course, this is an own error. We can't move out of the data that we don't own. However, if you do it with copyable types, the question is, what should you show? So should that, like the dereference of nref, should that require the own permission or not? And our initial design is that it would require the own permission. And as Xavier just asked, so we actually published this in our online book, And we got an overwhelming number of questions about this specific diagram. So people kept asking, like, why do you have the own permission? Like, I thought that if something was behind a reference, that you didn't own that data. And people are correct, right? You don't own that data, but you can copy out of it because integers, implement copy. So what we ended up doing is we no longer draw that own permission if something implements the copy trait. So we just drop the own permission requirement there. And so this is a good example of like getting the diagrams in front of people where they could sort of validate what we thought was correct, or in this case, they invalidated what we thought was correct, and we actually iterated on the design a little bit. Another confusion is between things that I will call prescriptive and descriptive permissions. So on this slide, this code type checks. I'll give you just a second to read it. And we can give this to a user and they might ask, can I put star num plus equals here? Like, can I increment the value of num there? And the answer is, of course, no, right? Num, like this is not a mutable borrow, so we can't, mutate the value behind it. And this is a prescriptive set of permissions because the num reference never had the right permission to begin with. So we can just never mutate that data. However, now if a learner is trying to think, how else could I mutate this code, they might ask, can I insert let x equals star num here? And this might seem a little interesting because the num loses permissions after that second line, but that's only because it's not used anymore. But that's where the liveness analysis comes into play. And so if they were to insert this let x equals dereference of num, then this would still type check. They're just extending that set of permissions, and that is the what we call descriptive permissions, and that it's describing sort of the liveness analysis under the hood. And this is something that we are still trying to iterate on because a lot of people find it confusing that they can modify the code to a point where they didn't have permissions anymore in the diagram, but it's just that the liveness analysis would extend the liveness of that reference one more line. Questions or comments on this slide? All right. Part of the reason we think it's confusing is, these permissions sort of represent an abstract interpretation of permissions across the code, but the liveness analysis does not fit into that abstract interpretation model very well. So there is sort of two separate things going on here. Another thing, so going back to the question on arrows, there's another thing that's confusing here, which is we only represent one arrow per set of permission changes. However, if you look at the second line, so we first create a new string, and then that second line, we create a reference to the string, but S has lost all of its permissions. Does anybody want to guess why? Right, we have the arrow going to the right, so we say that S is, it got borrowed out of, but then it loses read, write, and own permissions, but it should still be able to retain the read permissions. And of course, like the answer is that S is no longer live after the second line. So there are two actions that happened here. One is that S was borrowed out of, and then two, S is no longer used, and so the compiler also just says, oh, it's no longer live here. And so we lose all of the permissions. And this is another thing that we're trying to fit into our visual, visual space here to try and describe both of these actions going on. But it is a little confusing sometimes to learners as to why S is losing all permissions in this case.
I would actually argue,
yeah.
maybe if you could go back to that, like this is a pretty weird definition of liveness, because X is still live and X points to S. And you can't have a live thing pointing to a dead thing, like not in the normal sense of liveness. So
yes,
I would argue that's a Polonius quirk. And I guess my question, if I make this question, would be, have you considered just not showing this to users like that and actually making S still be live, because really it is live until the end of its scope?
That is a good point. And the answer is we experimented with it for about a week. and we didn't quite get it correct, so we didn't bother with it anymore. But it is still an open research question, and I agree that this is a Polonius quirk. And the correct thing to do would be to extend the liveness of S as long as X is live as well.
I don't know if that would be correct for Polonius, right? They might have good reasons to do it like that. But for
Well,
presenting
it would be
to
correct for
users,
us
that's what I
to
would
do
expect.
that on top of Polonius.
Yes.
Yeah. But it would be correct for the diagram to do that because it's a good mental model by which people can think about it, but the compiler doesn't necessarily have to do that.
Yeah.
I
Okay,
have
makes sense. Thanks.
one other question, that expands on Ralph's question. What about the drop thing for like S will be dropped at the end of the scope? Why does this not force it to be readable, writable, owned until the end of the scope?
Why does it not have to be?
But
I get your question. I will have to follow up on that a little later. I don't remember off the top of my head. But it is, I believe the compiler inserted drops behaves, slightly differently than if I were to insert a drop myself.
okay.
But I will have to double check on that. I don't think I can say precisely exactly how it works, not having worked on the code base in quite a while. So
I see. And the other thing is that it's 5 minutes to 8, so slight
okay.
time warning.
Yep. Okay, then I will hurry up. We just have a few more slides. So one open question that we're still trying to think about is how to deal with lifetimes. So in our permissions model, we actually created this F permission, which F stands for flow. And that is if data can flow from one place to another. So of course, in this example, that is okay. But if we, extend the example a little bit more, these references cannot flow to the output because we don't know whether or not they live long enough. We need to specify the lifetime parameters there. And with that, I'm going to switch back to my last slides and we will wrap up. Okay. So on to the testing part of the pedagogy. So we implemented this in our custom fork of the Rust programming language textbook. We have a lot of embedded quizzes in there. And what we did was we rewrote the entire chapter on ownership and borrowing, and we used these diagrams and the permissions model. And all in all, we found that people improved by about 9 percentage points in the tests, which is, it's pretty good, but people are going from 47% correct to 56% correct. So it's like going from really bad to just bad. And so we're still thinking about how we can improve from bad to better and then eventually onto good. And I'll just note, we weren't the first people to design diagrams like this. However, all of the previous work has a really heavy emphasis on lifetimes. And specifically, they emphasize sort of the linearity of lifetimes. So if you look at all of these diagrams, they draw lines across the code or boxes to represent live regions. However, it's really easy to construct examples where these linear lifetimes fall apart, of course, if you insert any sort of branching. So we also tried to experiment this by including braces around live borrowed regions, but it just didn't ever make sense when we expanded our code to handle branching and looping as well. So, okay, so moving on to the future, I would just say counterfactual reasoning for lifetimes is something that we're actively thinking about. So if you get a lifetime error, can we have a tool that says, here's a concrete example of a method call or, a call to this function that would produce undefined behavior in this case. So that is a little bit of a synthesis problem, but as well as a tool and IDE integration. How can we design an interface for that? I've mentioned several shortcomings of the diagrams and the permissions model in this talk. So improving those, especially around liveness. So, as Ralph mentioned, and Johannes, and then as well, those arrows trying to capture overlapping actions. I'm also very interested in designing diagrams or, debuggers for verification tools. I think verification is a space that is underrepresented in this demographic, and it'd be nice if we can get the education and proficiency of people using those tools improved. And of course, one thing that is sort of a far out research goal is if somebody were trying to make an AquaScope-like tool, but for a different analysis, the really painful thing is they'd have to re-implement all of the front-end code. But ideally, they would be able to specify some sort of database of facts about the program, and then you could automatically generate the diagram generator from some, specification there. So something that we're trying to think about is how we can create that program that will, allow people to automatically create AquaScope-like tools for their different analyses. And this is, I would put it under the umbrella of visualizing static analysis sort of at large. So to quickly summarize, we understand misconceptions of ownership by pulling questions from Stack Overflow, embedding these questions into our version of the textbook. We then designed our pedagogy to address the specific misconceptions and implemented that in a separate version of the textbook. And then we compare the pedagogy against the baseline, and we see that we improved by about 9 percentage points. The key takeaways is, of course, like design good APIs. That is my email address. I will publish these slides online if anybody wants to, access the links for them, but thank you again. And we have like 1 minute for questions, I guess, if people want to ask.
We can go over a few minutes, by the way. Nobody is obliged to stay, of course, but first of all, yeah, congratulations. Talk. I actually have a question maybe to start things off. You say that after all this work, you got a 9% or a 9 percentage point improvement in your survey. Did people get worse at any questions as well? Do you know if like it somehow hindered reasoning on some of the problems?
Off the top of my head, I don't remember, but I believe no. Okay. There were a few questions, especially those related to like lifetime parameters. And, there's one with a closure in it, which people didn't improve, but I don't remember anybody getting worse.
Okay, yeah, that was basically going to be my follow-up.
Yeah, and that's kind of why we're currently thinking about how to actually represent lifetimes properly in diagrams like this, because there are still quite a few questions related to lifetimes, and those are always sort of the most confusing thing that learners bring up still. So we've sort of addressed these ownership access errors okay-ish. We're still always trying to improve, but expanding this to lifetimes is another area of work we're interested in.
If nobody else has a question, I have another one.
I have a question, maybe.
Go ahead, Ralph.
On the technical side, but still. First, very cool. Always happy to see people use existing tools in a new way, and teaching Rust is one of these things which comes up all the time. So curious what will be next here. So you showed this execution earlier, right, where you had the vector state, I think. And you're skipping some part of the state there, right? Like actually there's this raw vec thing, and like it has a pointer and the length and the capacity and something. So do you have oh wow.
So that is what you're talking about.
Yes, I think. Oh yeah, the unique and the non-null, everything is there. Oh wow. What cap divided by 3? I don't know what that means. But my question was, do you have any kind of annotations that make you know what to hide, or like is like how does this work?
Yes. So in the playground version of this, we don't. But in the textbook version, which uses like the MDBook preprocessor, we actually have annotations that we can put on the code, which will tell us, it will tell the tool when to hide certain states. So you can say, for example, if you only wanted like L2, L3, and L5, I don't know why, but you could annotate those lines and say, only give me these frames, and then the tool will only provide those frames. And similarly, like you can hide these like steps on the right-hand side, and you can compress the tables as well to try
but
and make
on the state side, right? Like you showed, is the default thing that you're just showing all the pointers, or how does it work that it doesn't show all the other clutter?
In this scenario, what would be the
Like,
other
if you go back to the
quarter?
old view where it was like compact.
Mhm.
Yes. So what, like, is it showing, like, if V had other pointers in it, would it show them as well? Does it know to only look at the buffer field, or like, how does it, what does it, because this is a very nice picture. So I'm wondering how you got there automatically.
Yeah. If V had other pointers, what would
But
be a
V is
scenario?
a 3-field struct,
Yeah.
and you're only showing one of the fields.
I see your question. So essentially, how do we know to go from this view to this view, sort of
Yes,
by
how do you
default?
decide what to show and what not to show?
Yeah. Ooh, again, off the top of my head, I don't remember. We don't do anything too super creative. So we kind of just look at, if we have one reference here, we'll say, okay, we take that one reference and then we expand everything else down. I might have to get back to you on like the precise algorithm for it. Again, like we wrote this tool like a year and a half ago or so. So I'm forgetting a little bit of the details, but it's nothing too crazy. The only crazy thing is really like creating these differences in permission steps.
Yeah, no, that I can see how it gets difficult. No, I'm drawn to the very close stuff. So I'm wondering, like, if I would put a B tree and fill it with some stuff, how would that look? If I fill a hash map with a bunch of stuff, how would that look? Like, I'm just wondering what the, I mean, basically one of the things I'm thinking of here, maybe to like, so the borrow checking stuff is cool. But I also find just the state visualization stuff pretty cool. So there is this old project, which you might have heard about, called Preroda. I think that was the name, which is the thing that
yes.
Ollie.
Yeah, I am familiar with Preroda.
Right. So for those of you in the audience that aren't, it's a thing that Ollie OBK, fellow Miri maintainer, wrote a long time ago as basically, I think it's kind of a browser UI front end thing that connects to Miri and makes you like, you can inspect all the internal state and you can step through your program while seeing things. It's a bit like an ultimate debugger that has all of the Miri state. And you can see the provenance and of stuff. I have no idea how much was actually ever wide up. I didn't see it in action. I think it's not up to date for a while. But this looks a bit similar in the sense of it can I can also inspect the program state. And I could consider using this to debug my code, even my unsafe code maybe, because it apparently supports raw pointers because Vector has a raw pointer. So I was just wondering what's going on there and how that magic works.
Yeah. So what I can say is that an earlier version of these diagrams actually used Preroda to some extent, or we looked at Preroda to see kind of how they did things. And then we, try and condense things visually as much as possible. If you want, we can try like creating a hash map to see how that would look.
Probably B-tree map is actually more interesting. I think hash map is just one big array. I don't know how like it's untyped, so it probably would not show anything in there.
Okay, people are gonna have
map is doing some crazy pointer things. You should be able to take a list of pairs and collect it into a B-tree map if you want to make one that's a bit more interesting.
Okay, so if we have a list of pairs and we'll do integers to, what do we want to hash to? Strings?
I can just be integers and integers, I don't care.
Okay, we'll do integers and integers. Okay.
I'm curious about the internal structure of the tree. CXIV. But there's some really nasty raw pointer stuff in B-tree map, so I'm actually wondering if it would be doing anything.
This, like that. Okay. Do I have anything? People might have to correct my code if it's wrong.
You might have to do like .into_iter.collect.
We'll specify these as well.
No, yeah, but I don't think you would have to specify those, but it doesn't hurt.
Just to make it. No. Okay, so
sorry.
The answer is come back later and we'll implement it.
We dared the demo gods and they were not kind to us. Okay.
Yeah. So one of the things with the runtime diagrams is there's actually like we only really handle a subset. So one thing that I explicitly didn't do is if you insert like strings, like raw static strings, this will also not compile. So I know that we didn't implement this just because it's kind of tricky to look into that part of the code.
Yeah, they have an interesting representation now.
Okay, well, sorry,
Plus
that was a
performance.
little uneventful. Okay, Johannes.
Yes. Thanks a lot for the talk again.
Yeah.
I wanted to ask, because if I remember correctly, the way you originally like got your sample size population of people to run to like show this is you basically put an advert into the official Rust book. Which I guess means that you at one point talked to some people in the project about, I guess that they also kind of like exploring new ideas of like teaching Rust. Are there any like plans you have in the future for like making this into the official Rust book? Do they have any plans? Can you talk a bit about that?
So I believe the short answer is no, we don't have any plans into turning this into the official Rust book, partly because we like having sort of free reign of putting random stuff in there. And like having that experimental freedom is quite nice. So one of the tools that we're currently working on is like a trait debugger type tool. So it's kind of like a stepwise debugger for the trait solver. But you can also use it to generate similar diagrams about like the trait hierarchy in a library. And we've been thinking about, how can we rewrite the traits chapter to use that tool, and explain the trait solver a little bit more diagrammatically than just with prose and a bunch of code snippets. So to answer your question, I think the answer is like, no, we don't actually plan on merging it to the upstream book. We just like keeping it separately, but you would have to ask Will, who is the sort of core maintainer of the library, of the textbook, to know what his exact plans are.
All right. Thanks again.
Yeah.
Any other questions? Okay, it doesn't seem to be the case that there are any other questions. So I guess we can all thank Gavin again. And if there are any more questions, I guess you can show your email address again so that people can contact you.
Yeah, I'll just leave it there. Yeah, thanks again.